So we are working through Gaussian elimination, and we are first solving things by hand. So Gaussian elimination is a solution procedure for solving the problems, and today we're going to do one more problem that is solving things by hand. After that, we are actually going to see how to put systems of equations together based on the problem at hand. And this is actually the part where your engineering expertise comes into play. Like, do you understand physically what's going on, and can you formulate it as a system of linear equations? And that basically will be the part of our review that will end the part of our review where we're doing things by hand, and then we will actually start looking into numerical methods that can help us solve problems that are larger than 3 by 3. So if it's a 3 by 3 problem, you don't need a computer to help you. You can just solve it by hand. But you do also need to know the procedure in order to be able to program it in a computer so it can be helpful. So let's get going. Example I wrote down, and I'm going to write it down again anyway, last time, is the one with partial pivoting. So I have a system that is 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is minus 6. And 2x1 minus 3x2 plus 6x3 is equal to 2. If I were to start Gaussian elimination, we would create an augmented matrix. So I know that my augmented matrix for this problem looks like what? Can you help me?
0, 2, 3, 9, 6. Mm-hmm. 4, 6, 7, 9, -6. 2, -3, 6.
So if I were to start Gaussian elimination, what would I do? What would be my objective? To make it upper triangular. So technically there are positions here that I would like to make 0, and I can make things 0 by using techniques such as combining different, do a linear combination of different rows and then replacing one of the rows with that linear combination. The problem that we have here is that typically to get rid of this 4 and 2 in the first column, I would need that top position to work with. And what is in top position? Position 1, 1. There's a number sitting out there. 0. And can I actually multiply that 0 with anything to get rid of 4? No. Whatever I do, I will add 0 to 4, and 4 will remain unchanged. So first thing we need to do here is actually switch two rows. So I'm going to switch these two. So switch rows so we can start Gaussian elimination. Does switching rows do anything to the solution of the system? If I switch rows, will I do anything to the solution? To x1, x2, x3 that satisfy the system? Does anything change? No. So order is arbitrary anyway, so let's do that. So I have 4, 6, 7, 6 minus 6, 2, and 0, 2, 3. Whoops. No, 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 no. I gotta switch the entire row. So it's minus 6, 6. So good news about this is that this position is already 0, so I don't have to do anything. What can I do to zero out this 2 over here? What would I like to replace this row with? Or what would you like to replace that row with? You can be inventive. So there's a 4 here and a 2 here. 1/2? Then I'll have 7 over half. Can I ask you to? Yes, that would work. Yes.
-2 or 3.
Yeah, so how about 2 minus 2 times 3? Huh? Again, half works. I just don't want to deal with 7 over 2. So this is me being lazy. But again, there's multiple combinations that you could work with if you're doing things by hand. So let's do that. So if I do that operation, can you keep helping me here? So 4 minus 2 times 2, that is 0, as desired. 6 minus 2 times minus 3, that is actually 12. 7 minus 2 times 6 is 7 minus 12, minus 5. And minus 6 minus 2 times 2 is altogether minus 10, right? Is anybody checking on me? All right. Our next victim here is number 12. So what am I going to do? What can I replace this row with that will get rid of 12?
I would go R3 minus 6 R2.
That works. So row 3 minus 6. So here R3. So I'm guessing in differential equations you call these R1, R2, R3?
Yeah.
Oh. I can maybe change that in future. I didn't know. This is how I called it in my linear algebra class back in the day. So, I'm not going to mention when. All right, so what will I get when I do that? So I have a 0 because that's what I wanted to. And why is it important to work with second row and not, for instance, first row? So if I work with first row to delete something here, I'm going to reintroduce non-zero here. So I want to work with the row that has a 0 in this position. Does everybody see that? So it's important to work with this row and not with the first one. All right, so let's just do this. So 3, so minus 5 minus 6 times 3 is minus 23? No, minus 5 minus 18 minus 23. And minus 10 minus is minus 46. That's good, that works. So now we are in upper triangular form and we are ready for back substitution. So what am I going to do to actually get a solution to this?
So you solve the third line first, and then substitute the second.
So this is the easiest one to work with. So my x3 is 2. If you sing to my son, now, how old are you? How old are you? Anyway, that's the only thing. Or sometimes the best part is like he goes, 2. 1 and 2, same thing. x3 is equal to 2. Alright, x3 is 2. And then, so what do I do now?
Put it into the second equation, which is x2 plus 3x3, which is not 2, equals 6. So you get x2 is equal to 0.
And then finally the first one.
4x1 and x2 is 0, so nothing there, plus 2 times 7
All right. So our solution as a vector would be -5, 0, and 2. So I'm just piling it up in a vector. And can you check for me, pick an equation and check that this solution is really correct? Original equation, please. Indeed, so that's just 3 times 2. All right, so first equation seems to agree. All right, so that is it. That is a solution. So that basically resolves any issues when 0 shows up. Now, we could, in this process, switch our columns as well. Okay? So I can switch rows and I can switch columns. We will not do that in this class. If I actually switch columns to make my life easier with zeros, the problem is that then I'm switching who is called x1 and who is called x2. And I kind of have to keep a tab of that. I'm just not going to go there. Not by hand. You do that in our linear algebra. Sometimes, again, if you have a 0 and you want to switch, you could switch not just rows, but you could switch columns. But the moment you're switching columns, you're switching who are you referring to as x1 and who are you referring to as x2. And quite frankly, if I do that, I like leaving that to software to keep tab for me, not me by hand. Yes.
When you're given problems, will you tend to avoid like fractions and decimals in the numbers?
So I will tend to do that. Will it always happen? And will you make choices to avoid them? I don't know. So he was about to make the choice, which is a correct choice, as long as you execute calculations correctly. So I stopped him because I didn't want to deal with it. I didn't want to be the one dealing with it over there. Okay? But again, ultimately, if you really get crazy numbers, you probably made a miscalculation somewhere. So go back and okay? All right. Okay, so now actually let's move on and have fun coming up with problems to solve. So first one will be the classical problem of 3 reactors. Example. So this is now we're actually gonna how to come up or formulating systems of linear equations. Remember how the name of this course is formulation and solution. So we're going to formulate problems now. 3 reactors, and this is a classical flow problem. Anything can flow. Here we will do reactors, but you could just have pipe networks. And in oil and gas, of course, we have a whole lot of pipe networks going on. And basically, what you as an engineer are busy ensuring is that there is a steady state flow through those pipes. Okay? And of course, you would like to know what is the flux overall through those pipes. What do I refer to as flux? It's typically volume per time, or sometimes it's in linear measures, so it's just sort of, it has velocity to it, or it has units of velocity, but in that case, it means that that volume has been divided by the cross-sectional area you're flowing through. So you kind of, basically, when you talk about flux and you refer to it as meters per second, it means that through your pipe, a meter of volume has moved through, which is some cross-section. So you have 1 meter per second, okay? That 1 meter times whatever cross-sectional area is your volume that moved in 1 second through the pipe. So that is often the way to actually do that. So in order to get the flux, if you have it, if you have a velocity per time, or possibly you're just assuming it's constant, you basically integrate over that area to get the total flux through. So obviously, since we are flowing oil and gas around, we need to know a thing or two of how that works. And as an engineer, again, you want to calculate what the flux is. That will also tell you the velocity. Velocity determines the type of flow you have. And you will get to that in transport, but essentially you would like to have a laminar regime. If you're switching from laminar to turbulent, okay, it's that fast that it's getting turbulent, that is much harder to control. And as an engineer, you'd like to be in control. Now, the type of regime, like you're more likely to be the turbulent, the larger this pipe is. But the type of flow actually depends on the geometry you're flowing through, as well as the fluid itself, so its viscosity. So that's something that you will get into, but here I will just do the simple flow problem through the pipes. So what we are doing is we have 3 reactors. Okay. I'm going to call this one number 1, number 3, and number 2 over here. And they're reactors, so stuff flowing in is reacting and possibly something different is flowing out. Into this first one, I'm introducing 100 meter cube per second of fluid. And then from first one, stuff is flowing in this direction and this direction. So from first, I'm going to this second and third. So this flux that is coming in is splitting into 2. And I'm going to refer to these pipes that go between 1 and 3 as a pipe 1, 3, that is common. So I'm going to refer to this flux as Q. Volumetric flux is often denoted as Q. And if it's volumetric, then it's typically uppercase Q. And this is Q1, 2. Now from reactor 2, I'm flowing some of it after it reacted back into 1. And some of it into 3. And in 3, my problem is such, I'm not going into details, but I have to flow another fluid in there, 20 meter cube per second of it. And whatever is coming into this reactor number 3 from 1, 2, and outside is reacting and then flowing out, and this I call Q33. So Q is volumetric flux in meter cube per second, so I have volume per time. Now, if I'm having things in control, I want things in a steady state, moving at a constant velocity through the system, which means that there's no pileup anywhere. Wherever I have a reactor, which is kind of receiving stuff, whatever comes into that reactor per unit of time also comes out. So I don't have a filling up of this reactor that could possibly over time blow up or spill, right? So steady state, as an engineer, I want steady state solution. Okay? And first thing, I can look at this as an entire system. Okay. And so both on the system level, so this entire system of 3 reactors, I can see what's coming in and what's coming out. And every individual reactor in itself. So first, let's look at the entire system. What is the amount of fluid that is entering the entire system? That means all three reactors. 20. So I have 100 going into one and 20 going into three. So my entire system, on system level, we have in flux is 100 plus 20. I'm leaving the units out. So 120. On the system level, what is outflux? Has to be 120, but which one of these fluxes, how did I denote it? Q33. So I know actually that Q33 has to be 120. So that's the first thing I solved. Okay. So has to be for steady state. Now I also have to ensure that the same is happening in every reactor. Okay? So I want the same mass balance in every reactor. So my reactor 1, what is coming in? $100 plus Q21. Let me actually continue where I stopped. So what's coming in, what's coming out of reactor 1? Mm-hmm. So my second reactor, what is coming in? Mm-hmm. Q12. What is coming out? And then let's continue. My third reactor?
In the third reactor, that's Q23 and Q13.
And what's coming? And?
Oh, plus 20.
Mm-hmm.
That would be Q33.
Which is 120. We already solved it, so may as well. So those are our three equations. How many unknowns I have? So I have Q21, Q12, Q13. This one I already have. This one I already have. Q23. 4. I count 4 unknowns. Now they're not called X1, X2, X3. And guess what? In most of the problems you're going to solve, they're not going to be called that. Just like on your homework, there was a TA temperature that we were looking for, absolute temperature, and the problem was actually posed in terms of the Celsius temperature, and then you had to convert, and then there was that confusing saturation in there that you actually knew, but it looked like it wasn't known and all that. That's how real problems look like, okay? And you have to translate them to something that you know and that you see sort of theoretically. So technically you can, if you'd like, switch to calling this X1, X2, X3, X4, okay? Or we can just continue, and that might be a little easier here. So this is almost like my X1, X2, X3, X4, okay? They're just named differently, and you have to order them, and then you have to remember the order and all that stuff. So there's a little bit of bookkeeping always involved. Yes?
You have 4 unknowns, so you need 4 equations.
Well, we don't. So what's the name of such system?
It's
Underdetermined. Okay? So I have 4 great Q. I was about to comment on that. So we have 4 unknowns and 3 equations. So basically, I will not have a unique solution. Okay. So I will have sort of a parameterized solution. There will typically be one flux I can set or ensure to happen. So there will be no unique solution. And in this type of problems, that is okay. That is actually the way you want things. Because if you had precisely unique solution, and the only way to ensure steady state was to have one precise flux through each of these sets, you're the engineer ensuring that flux. For one, there is a transit problem at the beginning, even if you cannot just ensure steady state. It starts from 0, so it has to build up to steady state, whatever steady state is. Whenever you have pipes, they're empty at the beginning. To start filling them up, there will be certain time involved in getting to having a steady flux and constant velocity through all of them. Okay? So those are so-called transient problems in getting to steady state. You can hopefully get to steady state. And that's common always. Petroleum engineering in general. Ensuring this flux and this flux to be what you want it to be, okay, is not easy. And the only hand you have in the process is setting pressure. And then waiting for things to stabilize. Okay. So that's good. So let's now solve this. Okay. So I'm just going to now rearrange this a little and put everything that I know on one side and everything that I don't know on the other to formulate my problem. So I'm going to have Q21 from the first one minus Q12 minus Q13 is equal to minus 100. Because 100 I know, so I'm putting it on the right-hand side. From the second equation, I'll have minus Q21. And I have Q12, so I'm just going to make sure that I'm lining them up. And then I don't have Q13 in the second one, but I have minus Q23 is equal to 0. And then in the last one, I have Q13 plus Q23 is equal to 100. Because that was 120 minus 20. Solving this from here, you can either do standard Gaussian elimination, and I'm going to do that because you're going to get, when things are dependent on each other, sometimes a row of zeros, and I want you to see that. But you could also just by hand, one thing that I would do is here you express Q23 from here and Q23 from the other, and you can put it up in any of, so you can just by hand express what depends on each other. For sure, you're going to have one of them dependent variables, so you're going to express all the other unknowns in terms of at least one of them. But let's put it into a system of equations and see what do we do from there. So 1 minus 1 minus 1, 0, minus 100, minus 1, 1, 0, minus 1, 0, and 0, 0, 1, 100. So even though I don't have a full matrix and full diagonal, I still kind of want to get rid of this. So I can just add first 2, okay, and replace this by 1 plus 2. Or if you will, R1 plus R2. So when I do that, I'm going to have 1 minus 1 minus 1, 0, minus 100, 0, 0, interesting, minus 1, minus 1, minus 100, and 0, 0, 0, 0, 0, 1, 1. What's staring at me? So if I add them up, I'm going to get a row of zeros here. Okay. So this is actually, I'm just going to cross it over and say negative version of 2. So I have linear dependence. So I really truly only have 2 equations and 4 unknowns. Okay? 2 equations that are linearly independent and 4 unknowns. So basically 2 of these variables will be up to me, and the other 2 I express in terms of the others. So for one, I know that this, what was this, Q13 is simply Q23 minus 100 from this equation. So Q23 could be this one parameter that I set, okay? And I can call this one as the second parameter, and then I express things from there. So essentially, no matter what, 2 of the fluxes I set arbitrarily, well, the way I want, I guess. And the other 2 are dependent on them. So if I start from the second equation, that's essentially my back substitution. Okay, control. Save. Good. So if I start from the second equation, minus Q13 minus Q23 is minus 100. So essentially my Q13 is 100 minus Q23. So this is one of the ones that I'm going to leave as a parameter. And when I put things into number 1, now I know that my Q21 minus Q12 minus Q13, and I know that is 100 minus Q23, right? Is equal to minus 100. And double check on me that I did things correctly. Then my Q21 is minus 100. So it's Q12 minus Q23, correct? Did I mix anything up? So basically I have 2 of them, Q23 and Q12, as parameters that I simply set. Something positive, I hope. It could be negative. I just understand that if these things mean flux, if I have a negative number, I reverse the flow from what I thought it was. And that's it. This is the solution. So I have 2 parameters, and the other 2 are dependent on them.
So is it true that those 2 parameters will only be dependent on Q21, or could either one be dependent on?
Which 2 of them I set as parameters is up to me. But 2 of them are dependent on the other 2.
Okay, so
Okay.
in any
The
instance,
choice is
any
up to you. Yeah. It sounds some of it is also the way we kind of set up whatever is the first one we will be expressing is because that's how we were solving the Gaussian elimination. But it's really up to you who are you going to express. I could just say, well, my Q21 is a parameter, right? And express Q12 via Q21. That's fine. It's still the same system. All right. Now let's do another problem. And this one, yeah, we're going to start it. We're not going to finish it today. Is a model of a heated rod. And we are actually going to solve a differential equation numerically. And I will not ask you for analytical solution. And that numerical solution to a differential equation will ultimately end up being a system of linear equations. So that is also common, which again exemplifies why are linear systems so important, because a lot of things in physics I model using differential equations. So here's my physical, so this is again linear systems in applications. I have a rod, heated rod, in between two walls, and those two walls are uniformly heated. And the left wall is a temperature T0 of 40 Celsius degrees. I'm actually going to put a little bit of color here. T0 is 40 Celsius degrees. And the right wall, which I'm gonna call it T5, bear with me. It'll be obvious in a second. And they're separated by 10 meters. Okay, so they're a distance of 10 meters apart. So T0, T5 held constant. Differential equations, how do I call this type of boundary conditions? But I'm setting just a pointwise value to be something. 40 and 200. Dirichlet? Does that ring a bell? Oh boy. Okay. I am possibly ahead of your class here. And then what we want to do in every time, so what I actually know about equation that is governing the temperature distribution here, I also have another boundary condition, and that is my ambient temperature around this rod is 20 Celsius degrees, so it's basically room temperature. So that is my air or ambient temperature. And I'm not going to derive this, but basically the differential equation that governs this system is second derivative of temperature versus space. So second order derivative plus h. H is a parameter that I know. H time difference between T, A, and T. So this is my ambient temperature, so this is my boundary condition, and this is my temperature of the rod. This coefficient here, I'm going to give it to you. It is called heat transfer coefficient between rod and the air, and it's 0.01 meter. 1 over meter square, or meter to the minus 2. So this is heat transfer. Between the rod and air. So what this differential equation is saying is that sort of the second order derivative in temperature. So dt dx would be how fast temperature changes, and dt dx squared is sort of an acceleration of how this happens, right? It depends, there's a certain constant heat transfer coefficient that depends on the materials. It depends on the material that rod is made of and air itself, so there's a certain transfer coefficient here. And I'm gonna change faster if I have a larger difference between the temperature at every point and ambient temperature. That's what it's saying. So I'm gonna cool faster if I have a larger gradient in temperature. The problem here is that this is true at every point, okay? So at this point, the neighboring and so forth. And what I'm really after is what is the temperature distribution at every point that satisfies this transport law. Okay? So this is transport of heat. So is the physical context clear? So we're looking for T of x for every x. If you were in differential equations class, you would look for it analytically. Here, we're going to look for it numerically. The moment we're looking for it numerically, we are unable to solve T of x for every possible x because there's infinitely many between 0 and 10 meters. But we will discretize our line into a one-dimensional problem. We're going to simplify this as temperature at every point in one dimension. Okay? And for simplicity here, I'm going to discretize it so I have four points. 1, 2, 3, 4. Okay, this point I know this is my 40 Celsius degrees, and this point I know that's my 200. Okay? So I'm going to call this T1, T2, T3, T4. And to make my thing simple, they're all going to be delta x apart. So basically, I had divided my rod with these 4 points that I'm looking temperature. So all I'm looking for numerically is these 4 values, T1, T2, T3, T4. Could I choose more? Yes. And that's why we will program it later. Okay? So I can go to 20 if I want to. But let's just conceptually see how do we form the system of equations. So basically, my T1, T2, T3, T4. What is my delta x? 10 meters divided by 5. So it's 2 meters. Okay. So basically we will formulate, by discretizing this equation, we will formulate equations in T1, T2, T3, T4, and then we will look for solution of that linear system.